Welcome everybody to this session, to this talk by Alex. It's really a pleasure to have Alex here, and just to welcome all of you. And then I give my word to, because we are 5 minutes late, give my word to Marta, and then Marta will introduce Alex, and then she will conduct the rest of the session. Alex, thank you very much for being here. Marta, so that's your point. Thank you.
Okay. Thank you, Albert, and welcome everybody to this webinar. Today we have a very special speaker. We have Alex Arenas, and I'm going to tell you a little bit about him. So he is a physicist. He got his PhD from Universitat de Barcelona, and he then has spent some of his research time at the Lawrence Lab in Berkeley. Currently, he's a full professor at Universitat UBICS-complexitat. And he has done quite a lot of things. He has worked very intensively in complex systems throughout the years, and more recently he has had like several important contributions to network science. And because of his achievements, he has received in 2018, well, he was selected as a fellow of the American Physical Society. He has also received 2 ICREA awards from the Catalan government because of his excellence in research, one in 2011 and another one in 2017. He's an editor for the Journal of Physical Review E, and he's in the board of the NetSci Society and in the executive committee of the Complex System Society. He has advised 14 doctoral thesis, and he has published over 200 publications in international reference journals, which have received over 27,000 citations and totaling an age index of 63. And I think we are going to have a very exciting talk today about epidemics and mobility. So please, we all welcome Alex. We cannot clap, but we can clap at home. And well, I just like, without further ado, I give him the word.
Okay, thank you very much to everybody for being here. Thank you very much for the invitation from UBICS to give this talk. During this talk, what I want you is to learn a little bit about what is the role of mobility in epidemics and what has been our role in trying to help in this COVID epidemic with our approaches, and how these approaches are rooted in a kind of mathematical framework. Okay, then let's start. The first slide I have is a citation that is very nice to me and synthesize a little bit what happens at the very beginning of these epidemics. Is a citation from Daniel Bernoulli, one of the Bernoulli brothers, a physicist that was working on epidemics, and he did this particular paper that is considered one of the first epidemiological models. That was an attempt to analysis of the new mortality caused by smallpox and of the advantage of inoculation to prevent it. I mean, it's the very beginning of vaccination and the classical dilemma of vaccination. But one of the citations in this paper says, "I simply wish that in a matter which so closely concerns the well-being of the human race, no decision shall be made without all the knowledge which a little analysis and calculation can provide." And this is a little bit what is the role of modelers in all these epidemics, to provide this little analysis and calculation to inform authorities about the possible scenarios that they will confront, and then the political decisions are taken according to this information. Okay, then let me introduce a little bit what is the modeling in epidemics. I will perform a little bit classification of the epidemic modeling, and then I will present the kind of models that we developed during these last years. Okay, the types of diseases that one can afford from epidemiology are from non-infectious diseases or infectious diseases. In this bright plot, you have a kind of sphere with several classifications that I will scrutinize in the next slides. Non-infectious diseases, they develop during the individual lifespan. okay? And then epidemiology there studied the risk factors associated with the chances to develop this disease. But the most typical case and the ones that is most interesting for us are infectious diseases that can be passed between individuals, being these individuals human, animals, or plants, okay? And epidemiology in this area try to describe the main risk factors in the presence of infectious cases in a local population. Good. Then from this sphere, we will stay on the infectious diseases. In these infectious diseases, we can have infections produced by microparasites, which are small, are single cell, like viruses, bacteria, or protozoas. And there are others that are macroparasites that are bigger, like helminths and flumes. Okay? We will concentrate on microparasites, and the difference between these in modeling is already very important. Infections that are caused by microparasites, generally, they develop very rapidly from a small number of initial parasites, and the internal dynamics of the pathogen within the host can be ignored in a first approximation. This doesn't happen in macroparasites. They have a complex life cycle within the host that has to be modeled independently. That's important in order to propose a model what kind of types of infections we are dealing with. In these microparasites, then we have the possibility of direct transmission or indirect transmission. Okay? The direct transmission is the direct physical contact between the individuals that are exposed to the disease, and the indirect or vector transmission is when this disease is transmitted by a third party, like, for example, the case of mosquitoes. Okay? We will concentrate our modeling approach then in this part of the hemisphere, which is direct transmission. Good. Then, in this direct transmission, one of the important aspects to take into account to describe epidemics is what you have probably been learned during these pandemics, which is the basic reproduction number, which is called R. Okay? The simplest definition is the expected number of cases that are generated by one case in a population where all the individuals in principle are susceptible to get this infection. In a very simple term, for example, imagine that R is number 3. That means that one individual generates 3 infected, and these 3 infected can infect 3 each one of them. Okay? And this is the basis of the exponential growth that we all know nowadays because of the impact of COVID. Here are a few numbers comparing, for example, the reproduction number for influenza, that is around 1.4 according to previous studies, Ebola, that is around 2, and COVID, that ranges between 3 and, in cases, even 5, depending on the particular region in which this ratio has been measured. Okay, that for an example, how is the growing in the prevalence, the number of accumulated cases for Ebola and influenza? What you see is that a little difference in the value of the reproduction number can indeed perform different exponentials that if we compare, for example, for these same days, the prevalence of influenza, Ebola, and COVID, we see what is the danger of COVID. The number of cases is like explosive because of this basic reproduction number that is so high. Okay? Good. Then let's try to understand a little bit more about this R. This basic reproduction number can be computed on what we call in physics a mean field approach, which is a lot of assumptions where we say, okay, this is an infection probability per contact that we call beta. There is an expected number of individuals infected by an infected individual on a time period t that can be described by this simple formula. R is the product of the time window duration of this infection period, the period in which we are in contact with another person, beta, which is the infection probability in this contact, this average case, that is the average number of contacts per unit time, and rho s, which is the fraction of susceptible individuals that we see in the population at each time. Good. Then, from this basic formula that you can find in any epidemiological book, we already learned a lot of lessons. And the lessons are the following. To control the epidemics, we need to reduce this reproductive number below 1. That means that one case will generate less than one case in the next time step, okay? And this can only be satisfied by acting on the parameters that participate in the description of R. For example, we can reduce tau by early detection and isolation of cases. In this way, we separate these individuals from the rest. We can reduce beta, the infection probability per contact, by using drugs or by physical protections like the face masks or gloves, etc. We can reduce the average degree K by social distancing and confinement. I mean, separating the number of contacts that we have continuously in time, or reduce the fraction of the population that can be infected. That can be achieved by vaccination, by confining these susceptible individuals in such a way that they are not in contact, or by the well-known herd immunity or infection immunity. If you infect yourself and then you are in principle immune in a particular disease, then you can get also a reduction in the number of susceptible individuals. Okay, for the case of COVID, one of the points is that so far we don't have drugs and we don't have vaccination. And then if you explore these ways of reducing R, you will see that the basic elements we have are physical protection, which is the use of face masks and hands hygienization, and the early detection and isolation of people, trying to get social distance and confinement to break down these contacts. Okay? Good. Then let's go to the characterization of the disease itself. Usually we characterize the diseases by several states, and here I differentiate between medical status, which is the status from a medical point of view, you are incubating the virus or you are diseased, and the infection status that in a particular compartmental model that I am exposing here, you are susceptible, exposed, infections, and recovery. And all these different compartments are related to the time of infection in which you have in this blue area the growth of the pathogen in time inside a body, and the response of the immune system or the vaccination or drugs that attack the pathogen up to the point in which the individual is recovered because it's healthy or it's diseased. Okay? For this particular compartmental model, susceptible, we understand that there is no pathogen on the host, but the individual is susceptible to get the infection. In the exposed phase, we have a level of pathogen that is too low to be infectious, but probably there are no signs of infections yet. Okay? There is another compartment, which is the infection, in which the level of pathogen is high enough to be transmitted to others, is the part in which we are infecting others, and then is the recover phase in which the immune system has cleared the pathogen and the individual is no longer infectious because it's again immunized or dead. Good. Then, for this particular compartmental model, we use the capital letter S, A, I, R to define that we are taking into account this particular compartmentalization of an infection. In principle, you have several of these. The basic compartmental models that you will find in the literatures are this SIR, which is especially suitable for chickenpox, measles, and rubella. You have SIR, which is often a simpler version of the previous, in which the exposed class is ignored. You have SI system, in which some infections that, for example, happen in plants, which are very fast, and they remain until the plant dead. And there are others that are better described for a susceptible, infected susceptible model, like, for example, influenza or some sexual transmitted diseases. And there are more in which you have, for example, SIRS, which the recovery state is a temporary immunity, but then you get susceptible again. The first thing that you have to confront when you try to model an epidemics is to find what is the compartmental model that better represents the studies that you have been observing during the developing of the disease. But for the sake of simplicity, what I will do now is to introduce a very simple model that we started to play with 10 years ago with the group that is basically presented for the SIS model, in which you have beta, the probability of infection from a susceptible individual to infected, and mu, the probability of recover from the infection and get susceptible again. Let's see how it works. The main idea that we will expose in this approach is the following. Instead of having discrete states to describe an individual, if the individual is infected or not, we will want to describe the individual probabilities of being in one of these states that we described in the compartmental models. From this, what we will propose is a deterministic map for the evolution of these probabilities that you will see in the next slide. We will account for the specific contact matrix between the individual. Instead of an ensemble, we will use real networks, okay? Complex networks enter into play here when the contact matrix between the individuals is a network and not an ensemble. We will model this with a Markov chain, and from this Markov chain we can account for the order parameters that are more likely to be of interest for the population, which is the average fraction of infected individuals that we will have in time. Okay? Good. Here is how it works. First of all, we select the states that are in our compartmental models. We are represented, I recall you, the SIS. Then an infected individual here in your left can be, in the next time step, infected or susceptible. It will be susceptible with a probability mu, or it will become susceptible at a rate mu, to be precise, and it will continue to be infected with a rate 1 minus mu. Remember that those are probabilities and they sum 1. In the right, you have the possibility of a susceptible individual to remain susceptible. That means that you are not infected by anybody, or the probability to get infected. That means that you are infected by somebody. And the equations that describe this Markov chain is very simple. Are here written. The probability that a node I, an individual I, is infected at time t plus 1 is equal to the probability of this individual to be infected at time t and he doesn't recover, plus the probability that this individual was susceptible and it get infected by somebody, this 1 minus qi term. For the susceptible, we can plot exactly the same. What is the probability of an individual I to be susceptible at time t plus 1 is equal to the probability of the individual I to be infected at time t, but he recovers, plus the probability that he was susceptible at time t and he was not infected by anybody. This Q term, the probability that is not infected by, the probability Qi of being infected by somebody is the product of non being infected by anybody. Okay, 1 minus the probability of being infected by somebody. Good. These two equations can be written in terms of a single one, which is expressed here. Okay, and this is the basis for the modeling that that we are proposing in the group. Here, what we will have always is a dynamical system of n-map equations with n-dependent variables that can be solved simply by setting the initial conditions at time t equals 0, the contact matrix that we have, Rji, the infection rate beta, and the recovery rate mu. And we can prove mathematically that this system is a contraction mapping. That means that for every value of the parameters beyond a critical value Bc in the interval 0, 1, there exists a fixed point that is warranted by the Banach fixed point theorem. That means that we can solve this system by iteration and we will find always a single solution. Good. This is a comparison of the model against a Monte Carlo simulation. Monte Carlo simulation is a kind of agent simulation in which we simulate every particle, every individual, according to the rules of the epidemiological model that we have proposed. And here I present the density of infected individuals, rho, in the y-axis, in front of beta, the probability of infection that we have for a certain disease. This theoretical word represents that the SIS model with a particular recovery rate mu equal to 1 in a network which is power law distributed with 10 to the 4 individuals and exponent 2.7 is plotted here and in circles for the Monte Carlo simulation and the continuous line for for the microscopic Markov chain approach that we are proposing. And this is simply to corroborate that the accuracy of the model against a particle simulations is pretty high. Okay? If we do this not only in terms of the particular density of infected individuals, but about the spatial distribution of these individuals, we did this at the level of the full world for the epidemics that started in Osaka in 2011. And we used Monte Carlo simulations and microscopic Markov chain approach. And the red points are the infections that we expected in the world according to the particle simulation model, and the same plot for the theoretical purpose of our model. And the agreement is pretty good. The error is lower than 5% for this scale. Okay, good. Then how do we calculate things there in the microscopic Markov chain approach? In principle, one of the things that are more interesting in epidemiology is to know the epidemic threshold. That is the value of the infectivity parameter from which the epidemic starts to be different from zero. Okay, this is a phase transition in physical terms, and it's pretty simple to compute this from our equations if we impose the stationarity or the calculation of the equation at the steady state. I mean, if we impose the probability of a node I to be infected or not independently on time, you see that in this first equation there is no time anymore, then you can linearize the equation near the critical point for values of pi that are different from zero but very, very small. That means that you can linearize the product for the QIs, and the product becomes a summatory, and the first order expansion of these probabilities can be computed, and what you get is the usual solution in any epidemiological compartmental model for the critical value of the infectivity parameter. That is an eigenvalue problem represented by this matrix R multiplied by the vector P of the probabilities for every node, and is equal in this case to mu, the recovery rate, divided by beta, the infection rate, multiplied by the same vector. Solving this eigenvalue problem, we obtain what is the critical infectivity from which the epidemic becomes endemic. Okay? Good. But now we have to go to a next level, because we will have metapopulation instead of individuals that are different patches, geographical locations, and the individuals are moving from one to the other, and this distribution, this geographical distribution of the infections is very important to assess what will be the outcome of this epidemiological aspect. Okay? Then, for this, what we did a couple of years ago was to adapt our previous model for individuals to metapopulations. Metapopulations in which we impose recurrent mobility. Essentially, recurrent mobility means that every individual has a place, a house, and this individual commutes to a certain place to work or whatever, and he comes back home. Okay? So then, if we label each patch by I, you can apply the same equations that I presented before for the probability of one individual to be infected to a conversion in which this probability is the density of the probability of infected individuals in this patch at a certain time. Then the same equations are written down in the same way. Now the only thing is that we have this term, which is the probability that a healthy individual that is associated to a certain metapopulation is infected at time t has to be described. To describe this equation as a function of the mobility, we simply consider the following aspect. With a probability lower p, which is 1 minus p per capital pi, that means that the probability that an individual doesn't leave his patch and get infected with a probability capital P, or the probability that this individual moves out of the patch with probability lower p, and the sum of the probabilities of being infected at each one of the patches J that can be destination of the movement of this individual. Okay? The next step is we have to assess what is the probability of an individual I to be infected in any other node. To do this, we write down the same structure of the probability that you have seen for individuals, but here you have to take into account what is the density of individual that moves from one place to the other, which is the exponent NGI, okay? And this exponent can be expressed, again, in terms of the probability of not moving, 1 minus lower p, plus the probability of moving p multiplied by the flows that we have in the network of movements. If we wrap up everything that I have explained up to now, what we get is, again, a new set of equations that are described here, okay, and that can be computed and compared with Monte Carlo simulation. Here we present these simulations. The points are the Monte Carlo simulations, and the lines are the theoretical predictions that we have with the model that I have proposed so far for metapopulation. In two cases, the SIS model and the SIR model. In the SIR model, remember that after the infection you get recovered and you are susceptible again to get the infection. As you observe, the accuracy of the prediction is very good so far. Okay, what about the epidemic threshold? How we compute it in this new scenario of metapopulations? Very similar to the way in which computed the same for single individuals. We go to the stationary state, we write the equation in the stationary state, and we linearize all the products for very low values of the incidence. That means that we are close to the transition before this epidemic grows up and gets endemic. We can linearize and get an expression which is pretty simple to develop. After some algebra, you get a formula approximated or linearized for pi I, which is the main object describing the probability of being infected in another patch. And then you wrap up a matrix like this, and let's try to describe what these mathematical terms are representing. Essentially, what they are saying is we have several populations and individuals I and j. Okay, the first term that we find here in this solution is the probability of getting infected in the same patch because of other individual infected infection. There is a second term which is symmetric. That means that we have an infected individual in patch j, and I am a healthy individual in patch I, and then I move to this patch and I got infected. And of course, you have the symmetrical way in which the individual comes to my place and he infects me. Okay? And then the last term is the term in which there is an infected individual in J, I am a susceptible individual in I move to a third-party patch, and then I got infected there. Okay? These three terms are essentially wrapping up all the process in the recurrent mobility aspects. Then, if we summarize the previous equations, then we can convert this problem, again, linearizing to an eigenvalue problem, essentially equivalent to what I have presented for a single individual. The last equation is an eigenvalue problem with this matrix N, and N contains all the information about the epidemics and the mobility that you are observing into the system. Then the critical value of the infectivity is simply the inverse of the largest eigenvalue of this matrix M, as in any other compartmental. Okay, if we go to synthetic networks that are homogeneous in degree, this is Erdős-Rényi graphs or scale-free networks, what we can compute is what is the critical threshold, beta C, that we observe for different values of the mobility, that here is represented by this lower p, from 0, that is static, no mobility between the patches, to 1, in which everybody is moving from each patch to any other. And what we observe here is interesting. Of course, as we go more and more mobility, the critical threshold goes down. That means that the diffusion of the epidemics, the movement, is in favor of this propagation of the epidemics, which is somehow trivially expected. But when we went to real metapopulations, and the first study we did was in the city of Santiago de Cali, what we have is something different. Look, here our data were 22 districts of the city of Santiago de Cali, which is habitated by 2.2 million people, and we got 10 to the 5 trajectories from mobility patterns. Okay? And then this proposed a network that I have numbered here for the different districts with different flows that represents the people that goes to a certain place and go back. Applying our formalism to one of these districts, as you observe, here I plot the result of an agent-based system that is the the Monte Carlo simulation, and the microscopic Markov chain approach that we did for a single patch. And here you observe for the different nodes in the x-axis what is the evolution of the epidemics in time. And this was, for our surprise, something very interesting, because this is the first time that instead of computing the critical value of the epidemics, we compute the dynamics of the epidemics, how they evolve in times. And it was, for our surprise, something very precise, because it could happen that our description is correct for the average in time of what is going on in a place or another. But the precision or accuracy in getting information about the incidence of the epidemic for every single node that in time it's so accurate compared with Monte Carlo was something that we didn't expect, and let's say that leveraged our model to a next level in which the time evolution was also predictable. Good. Then, for this case of Cali, we present here the same aspects as before, in which, as a function of the mobility P, the lower P, we compute the critical threshold. And here you have something very interesting. Look, for this part of the plot, the ratio between beta and the critical beta at P equals 0, which is the representation that we have, is growing up. That means that the critical threshold, instead of going down, that means that it's more dangerous, the epidemics, it goes on the other side, okay? The critical threshold is larger. This is somehow an epidemic detriment, which is favored by mobility. And the revelation of this aspect of the problem was very surprising. We didn't expect to observe this epidemic detriment, and we try to understand what is going on. It's a problem, it's an error of the codes or the modeling, etc., or is something that is intrinsically real and admits a physical explanation. And this is what we did. We did an asymptotic analysis of our equations for P very low, P going to 0. And what we observed is that there are 3 different regimes that we can expect in the evolution of the critical threshold for different values of the mobility and for the different structure of the network. In this plot, I show what is the maximum eigenvalue of the matrix that represents the mobility and epidemiological parameters as a function of P, and we see that we can have in the particular area of interest, that is at least one individual infected. This is the lower limit 1 over n max, and the maximum limit of P equal 1, total mobility, that we can have something that always increases, something that decreases and then increases, or something that always decreases. These different regimes can be found theoretically, and the good news or surprise was in the real cities we can apply these. We apply for Santiago de Cali, for Medellin, and for Bogota, in which Jesus and his collaborators have a lot of data, and we use this in our models. And we found that several different cities could have different types of evolution of the critical threshold. In Santiago de Cali, we have this threshold that goes first up and then down, and in Medellin is always in favor, and Bogota, the mobility of making the spreading of the process beneficial from an epidemiological point of view. Okay? Okay. You can ask here why. Why is so? I mean, why diffusion? Why mobility should got in such a way, in the sense that the more you move, the better for the epidemic not to be so dangerous. And the very reason is that mobility is redistributing the population all the time. Okay? And this redistribution of the population is a key point to understand how the epidemics will impact a certain area. Okay? Then, the more redistributed gets the city according to the recurrent mobility established, the better for the epidemic spreading process to be not so harmful. Okay? That's the very reason. Okay, with all this information at hand, what we thought is that perhaps we could apply this this kind of modeling to the modeling of the COVID. And this is what we have been doing in the last 6 months. We started very early in February, 5 months more or less. And here are the results of the model that we have been using to compute what happens with the COVID in Spain. Okay, this is the compartmental model we determined. Here you see it's a kind of SIR model, but here in the epidemiological part, which is this part here, we have susceptible individuals, exposed individuals, not yet infections, but we included from the very beginning this new compartment, which is A, which is the asymptomatics. Okay, people that is infections, but they don't display symptoms or they have mild symptoms. And this, for me, is one of the key points of the modelization of COVID. From the very beginning, all the models that were considered SIR simply didn't distinguish between this asymptomatic state. That is very important because the fact that you don't see any symptoms of the infection preclude you to be identified, in the health system or by yourself and make a self-isolation or trying to understand what is going on there. Good. And for the part of the recovery, from the infection to the recovery, what we have is a set of clinical dynamics that we put again in our compartmental model. Why we did that? Because we identified from the very beginning that the problem of this explosive growing of COVID will not be especially the number of deaths that you will have, because it will depend on the lethality of the virus, and the lethality of the virus didn't show to be so high at the very beginning of the epidemics, and now we know that it's more or less double the factor of the influenza, but still the problem was before. The problem is if you have to provide assistance service in the health system, you need to know what is the volume of people that will arrive to the system and what is the capacity of your system to, let's say, provide service to these people, okay? And this was especially heavy for the ICU systems. If you need intensive care, and in the case of COVID, you know that the critical patients need assisted breathing, etc., then this will be a point in which if the exponential of the number of cases, even though a few percentage of these cases will go to the intensive care, if you don't have enough, and this is synchronizing in time, I mean, it's explosive, those patients will arrive at the same time, more or less, you have the risk to block totally the health system. And this is why the clinical dynamics in these compartments is a little bit more sophisticated, and we have different compartments to see what is the course of action when you are identified from infection and you get in this part. Okay? Then the first part, the epidemiological important existence of this asymptomatic, because they will behave like an exposed individual. You don't know that you are infected, but you are infecting already. Okay? And then once you are infected and you know, you start the process in the clinical dynamics, in which you will be hospitalized, probably taking care and assistance of intensive care, and in some cases you recover, in some cases you get. Okay. The model has also another characteristic that is interesting, which is age structure. For these different compartments, you have always a superscript that we call G within the age stratum. Okay. At the very beginning, we incorporated 3 age status: infants, adults, and elderly. And they were from 0 to 25, 25 to 50, and 60 and 60 up. And this is very important because from the very beginning, the studies of COVID show a different impact at different age stages. Okay, and these different impacts are captured by this age structure of the system. You can incorporate as many age structures as you need in this model, provided you have data about the interactions of these strata. This is what we write here like this: C in asymptomatically infected, contacts between different ages. I mean, how many infants, how often infants contact adults, adults contact elderly, elderly contact infants, etc. All these combinations. Okay? Good. Then, how the mobility and mobility data and mobility restrictions enter into the play in this epidemiological system. What we did is the following. We got mobility data gathered from the Instituto Nacional de Estadística for normal weeks and weekends, okay? And these data represent what is the normal mobility of people without the epidemics on top of this, okay? Then, if you execute some kind of confinement, then a fraction of the population is confined in the household. This fraction is kappa 0, the fraction of the population that we will consider as confined. The confined population keep in contact with other confinement household with a probability, which is phi, and this is the probability that these contacts, you have to go out of the household to buy groceries, etc. And then there is a probability in which you will contact others even under confinement. Okay? And the non-confined individuals, those that they go work normally because it's essential, for example, you know, the case in Spain, they reduce the number of contact due to the social distancing by a fraction delta, in which in this social distancing we can include the lower number of contacts and the lower infectivity that you have by wearing face masks. Okay? Good. The full set of equations, if you take into account this model, is developed exactly in the same way I explained for the SAS. They have these aspects. I will not enter into the details because mathematically it's a little bit cumbersome, but the same ideas, same procedure that I have explained so far. No magic there. Okay? Then we started from the very beginning to use the model to assess what was the risk of having COVID cases in different municipalities in Spain. Here, provided the data from the National Institute of Statistics, we have the demography and the mobility between the different municipalities in Spain that are here represented by the geographical region. Okay? And we were able to predict in time how these risks was increasing in Spain. The first idea that we had was to use this kind of information to let know policymakers what was the situation and what was expected to come. Okay. At this moment, when we were doing these maps, this is a particular map because we had a website and we started from the very beginning, ends of February, to represent this map of risk. No attention was paid to this, and the classical mantra was, we have very few cases, it is impossible to have COVID in Spain, there will not be community propagation, etc. You know. Good. The second thing that we did is to evaluate what will be the load of the health system for every region. We have at the level of municipalities, but we can condensate it at the level of provinces, according to the data that they reported about the number of intensive care units that you have into the system. And here, these percentages that we represented, we were assuming that all the intensive care system was absolutely devoted to COVID. I mean, no other disease was treated there, which is a very optimistic situation. And even in this case, we observed already the danger that we will face in the next week after 18th of March, according to the load that you expect in these different regions. And as we see it at the end, these predictions were very, very accurate. And even though the health system started to grow itself, putting more beds, more intensive care units, etc., in some places, they double or even triple the number of attentions that they can afford. Even in this case, the health system suffers a lot during this week, and as you remember, it was the worst part of the epidemics here in Spain. Good. Then we can use this information to, according to the load capability of the health system, to see what happens if you don't take any restriction of mobility measures, which is the red line. As you see the row exponential, we break the health system in some date. With the restriction that the government imposed, the conditions were much better. I mean, we started to flatten the curve, but still it was a real danger of breaking out the health system. And the health system in the normal conditions was totally broken. The thing is that the system tried to grow itself very, very quick in order to absorb all this capacity. But what we observed from the very beginning is that the restriction of mobility was total, the total lockdown. That means that only essential services are running. We can bend the curve and stay in a situation which is much more convenient to control epidemics. Okay. In the case of the COVID, as you remember, I represented the mean field structure of the basic reproduction number R presented before. If we compute this for COVID using our model and the patch and ages structure of the system, this R is for every patch I at time t and for every age stratus G, we have this expression that essentially combines the same parameters. The time of the exposition multiplied by the infectivity, in this case for asymptomatic and non-asymptomatic individuals. And in the other part of the equations, what you observe is the product between the probability of contacts that you have between these different ages stratus and different patches, and the proportion, the fraction of susceptible individuals that you have for every age status. Okay? This is the evolution of R for the different age status, adults, young, elderly, and the average for the different confinement levels that we have in Spain, represented here in the inset, for the different data, for the different dates. And one of the things that we observe is that, okay, after imposing these measures of mobility restrictions, the value of the basic reproduction number goes down to 1, but still it can go up, okay? One of the observations here is that one strategy to control this epidemic is you can keep the average of the basic reproduction number below 1, even if one stratus or one patch have a value of R that is larger than 1. And this is very interesting because it offers different techniques of controlling the epidemics. If you know that there is a part of the population in which the infection is not so high, you can try to get there herd immunity and still having a value of the basic reproduction number for the whole system which is below 1. And the same that I say for the age stratum can be said for the patches. I mean, you can afford some of the patches to have a large R as long as you are able to control that the average of the rest of the patches is below 1. Okay? Good. These equations that we obtain analytically is very complex, I will say, because it incorporates all the compartments, all the patches and all the age stratum. And here, to graph the physics, what we did is a simple exercise. We neglect the heterogeneity among subpopulations, and we assume that the pool of susceptible individuals will remain constant during an intervention. Then you can simplify the equation, the full equations that you have at the top of the slide, and you get something which is simple, but moreover, it clearly describes what is the role of confinement in the evolution of R. And we see here that the dependence of the basic reproduction number on the confinement kappa 0 is quadratic. That means that this confinement will force a phase transition in the incident curve, and that the values of this reproduction number are non-linearly related to the confinement. Then you cannot say, okay, if you go double the confinement, you will lower R by 1/2. This is not the case, okay? Because in this case it's quadratic, and the transition that you will observe is non-linear. Okay? Here we plot the confinement level in the y-axis and the social distancing delta, which is a measure of the use of face masks and the isolation of contacts, the reduction of contacts. And we identify two regimes. A bending regime in which you can flatten the curve over RT equal to 1, and a bending regime in which you will bend the curve below R equal to 1. If we put for a value of the social distancing of 0.4 that we calibrate with the data that we have observed after the lockdowns, and it was a pretty good value for this parameter, what we observe is that the incident, new cases, the new infected, as a function of the confinement in time, in the x is dates, you see that this curve for no confinement, which is represented by kappa 0 equal to 0, is the blue curve. Look at the values that you have in the y-axis. I mean, we arrive to millions of infected. This is what happens if you confine 20% of the population, 40% of the population, 60% of the population, etc., up to the full population. And you will see that in a value that is between 0.5 and 0.6, you already have a bending of the curve. You have an inflection point and the curve starts to go down immediately, okay? This was the goal of the government, and it was the goal of many of the governments that applied the total lockdown, is to bend the curve as soon as possible and go to the decrease on the number of cases per day, and then provide some air to the health system. Good. These are results of the predictions of the model already, okay? Here we have calibrated the model up to March 30, okay? And here is the curve. The points are the observed cases. In the top left, what we have is the daily number of deaths that you expect. In the right top, what we have is the incident, the number of new cases per day. In the top level, what we represent are the types of lockdowns that we have been applying in Spain, the partial lockdown, the essential mobility only, back to the partial lockdown, and then the process in which we leave people to go out for running, etc. You know, all these aspects, okay? The continuous line is the prediction of the model. The front that you see is the interval of 90% confidence for this prediction. And in the bottom, what we represent is the same data, number of new daily deaths and number of new daily cases. But now, instead of having a global vision for the whole country, what we did is for different autonomies that we have in Spain, the model and the data are confronted, and in the diagonal, it means that the data and the model are pretty close, okay? And here you see that for the number of deaths, that was the value used to calibrate the model, the precision is very good. And for the number of cases, it's a little bit more noisy, but still we have a pretty good vision of what was going on day by day. Okay. Finally, I want to conclude by highlight some of the ideas that I have presented here for this model. The model seems to be suitable for monitoring the evolution of an epidemic outbreak, especially in the initial part where the acceleration goes on. And after this part, you have to calibrate according to the mobility restrictions that you have. It gives accurate information about geographic spreading, and it pinpoints the regions that will be at risk. And they are useful to project new scenarios, evaluating the degree of lockdown that you need to go to a situation in which you bend the curve, and you can compute what is the time that you will need up to a point in which the control of the mitigation goes to the suppression of the epidemics, which is the final goal. Okay? There are some limitations, of course. We have mean field approach within the patches. The patches that we have been using are municipalities, which was the finer grain that we found on the data. We consider that the individuals are indistinguishable. I mean, we don't have that every person that moves has like a code, and we know that this the same person that comes back. This indistinguishability of individuals is a limitation of the model. And in this particular model that we have proposed so far, the international mobility was not included. And this is something that we have to include because, of course, if we open our borders to people from any part of the world to come here, we have to consider the particular infection state of these countries, of these regions, and the income in and out of our region of interest. Okay, and finally, to thank the dream team, the people that has been doing all the work and make possible this, that is Sergi, Jesus, Clara, Joan, Benjamin, David, and that's it. Thank you very much to everyone.
Thank you very much, Alex. So now, thank you very much. It was a very engaging and beautiful talk. Now we have time for questions. Yeah, people are typing virtually. I don't know if you can see it. Maybe check. So we already have some questions. So what I will do is I will make people who have a question, please write it in the chat so that I can make you a moderator so that you can ask it personally to Alex. Okay. So the first one, and I'm working on it, is Eduard Viva. And so please, Eduard, if you can connect your camera and your microphone, or at least your microphone.
Let's see.
Yes, working.
It's working? Yeah,
Yeah.
okay. My question, well, in fact, I have two questions. The first one is about the asymptomatic. Whether in your model you include the possibility that asymptomatic evolve to recover it without being infected, and whether this could explain why the number of people that generates antibodies is so low. Let's say it's only 5–10%. If this can be explained by the fact that the virus is transmitted with people that they simply don't get infected, but they are asymptomatic.
For the first question, the asymptomatics, yes, they can go directly to recover. They don't have to be identified. This is something which is important because in the compartment of asymptomatics, we are able to compute how many people are needed in the asymptomatic cases to have this observation of detected cases. Okay, and at the very beginning of the process, it was a little bit surprising because we were accounting that the number of asymptomatic people that will be running there, it has to be 7 or 8 times the number of detected cases. Okay, but at the end, this can only be cross-checked if you have a seroprevalence study in which you pick the population and you look for the antibodies in the system, and you make the statistics of how many people are supposed to have been infected in any of the states, asymptomatic or with an infection with its symptoms. What we did is to compute what is the level of seroprevalence that we will expect in the population. And before the study of the Spanish government goes out, we already predicted several weeks before that the expected number of immune people were around 5% in the whole population. Okay, that was confirmed at the level of Spain for a particular study that they did at the level of the different autonomous community, and somehow it makes the difference between disinfected and these asymptomatics to be more credible, let's say, in the model and cross-check our predictions at this point.
So if I understanding, asymptomatic, they don't generate antibodies, or they do generate?
We assume that they do generate.
They do generate, okay. Okay. And then just a second question. Does your model explain why now the situation, the number of patients in ICU and the number of deaths, of people dying is decreasing, and we have somehow released most of the constraints? So it's only probably it's only the fact that we are using, some people is using masks enough to prevent again the spreading of the virus. And
that's a very good question. I mean, we are in the part of the curve where the incidence of these epidemics has been controlled because of the lockdown. I mean, all the people was closed during 2 weeks, okay, and that makes this infection eventually impossible to contact other people, impossible to diffuse, let's say, okay. When we open, the virus is there and the infections will grow up again, okay. But now we are in a different situation. We are protected. We now use masks, we have these distances, etc. And as far as people is respecting these measures, we can control these numbers. The problem is that if you miss a little bit these security measures, let's say, right, these protection measures, etc., then what you will have are little outbreaks, okay? And this will happen during many times in Spain, and the solution is to control the contacts. I mean, the only thing that you can do is to contain this chain of propagation. Okay, this is why it's so important now to have this contact tracing. Otherwise, because the mobility is open again, we will start grow up, and there is no way to avoid this. Okay, then we are now in hands of satisfying social or physical distance, let's say, and the use of face masks, and in cases of outbreaks that they will appear, it's unavoidable, then you need a very good contact tracing. Because if some of the people that was infected in a barbecue, in a party, in a particular factory, etc., they have contacts outside and they don't recognize these contacts, and one of these contacts not infected, because the mobility is open, these people can go any place in the country, right? And he will or she will propagate the infection again. Then the situation now it's critical, because it's very difficult to control this. We have these manual tracers which are doing a fantastic job, but a very difficult one. And at some point it will be uncontrollable, and these small outbreaks can become a big outbreak, and this will be a bad situation, because that means that we start from the very beginning.
Okay, thanks, Alex. So we have another question from Kim Zalbo.
Thank you very much for your presentation, Mr. Arenas. It's been a pleasure. My name is Kim Zaldo. I'm a predoctoral researcher at the Autonomous University of Barcelona, and we are currently working with, or I'm trying to studying the COVID infectivity rate and mortality rate in Catalonia. And we are using land use and land cover data and socioeconomical data to try to characterize the nature of the healthcare by the basic areas in the pre-lockdown situation. My question is about the data of mobility, or trying to gather reliable data about mobility. You said you use data from INE, And which kind of data did you use? For example, average from the previous year, or which kind of data did you use?
At the very beginning of the model, what we were using are the origin destination matrix that they provide for all the municipalities larger than 100 individuals that was recorded in 2011. Okay. After that, they have this agreement with the phone companies, and they have particular mobility from every place to every place from these companies, and they released this origin destination matrix later. Then there was Google also offering snapshots of the mobility, and there was this project by Facebook that is called Data for Good, in which you have different densities and you have the mobility. And there are several companies. I know that one of them was working with the people in UBICS in Mallorca, and they have daily mobility traces, etc. I mean, the problem with the data is usually the same. I mean, it's very difficult to gather the data, but the data is there. Okay. The problem is that sometimes people is not eager to share the data, and they want you to pay, or they say that it's confidential. It's a nightmare. Okay, but the data is there. It's not a problem to have these origin destination matrices.
Thank you. Thank you very much.
Okay, thank you. So there is another question, and I'm going to ask this one. It's by Romualdo Pastor Torres, and he's asking, well, he's thanking you for your talk, and he's asking whether you are trying to explore what could happen if you gradually open schools or I'm assuming other similar kinds of institutions. Are you trying to explore that?
Well, we're trying to explore that, yes, at this moment, but it's like a micro scenario now. I mean, the opening of a school has, okay, let me explain. If we open the schools, in terms of the mobility that will produce, when I say schools, I say schools, universities, secondary institutes, I mean, everything, okay? This is more or less, if I remember well from the data of INE, is almost 35% of the mobility. That means that there's a lot of people moving around, okay? But now the problem is what will happen in this concentration of people at clusters. Then we have this micro scenario in which what will happen in a particular room, okay? And if we can describe precisely this well mix in the school, we will try to go out of this school and see what will be the propagation around the rest of the geographical areas. Yes, this is a very nice problem and difficult scenario.
Thank you. We have another question by Ernesto Estrada. Ernesto, you can open your camera and your microphone.
Share video. Can you see me now?
Yes.
Yeah. Okay. So thank you very much, Alex. It's a great talk as usual. I have a sort of intriguing question. So there is a recent preprint by Mario Castro, Saul Ares, Jose Cuesta, Susana Manrubia about the predictability in general of compartmental models. So the paper is predictability, can the turning point and the end of the expanding epidemics be precisely forecast? And the abstract simply say, no, they can't. And they say, well, that the problem is because of the susceptibility to initial conditions, and it's not a matter of the number of compartments that you use, it's not a matter of the quality of the data that you use. So in your case, your model, I think you use a very realistic compartments and the data that we have, and you made some forecasting for the situation. So how do you manage this problem of unpredictability, which is intrinsic to these compartmental models?
This is a very good question, but I think that there are several kind of level of abstractions of the model in which you can say things or you cannot. It is true that the unpredictability is inherent to the stochastical aspects of the model itself, but it doesn't mean that you don't have a statistical way to predict and have confidence intervals for these predictions. The question is not this. The question is, these confidence intervals will grow up to a point in which everything is possible? The answer is yes, depending on the point of the fluctuation, the stochastic fluctuation you have in your system in a certain time. Okay? Then, our experience with the model is that it's pretty accurate in, let's say, big numbers. Okay, if you want to know the number of infected individuals in Spain, it's pretty predictable. If you want to know the number of infected individuals by community, it's pretty predictable. Even at the level of municipalities, it's pretty predictable. If you go to lower levels, my prediction is nothing, because I don't have a way to go down to these scales, okay, of movement, of interaction, etc. Everything becomes a stochastic here, and the stochasticity in this area is very, very high. But essentially, I take advantage of your comment, Ernesto, because there is a lot of I don't know, discussion about the usefulness or not of models to help in the pandemics, etc. Okay, here it goes my idea. I think everything is true. I mean, at the moment that you try to do something with mathematics, okay, which is a theoretical aspect in which you don't control all the parameters, etc., it seems that you can fail or not, okay? But what is the alternative? I mean, it's we do nothing. I mean, we don't use models at all. We think that this is no worth to put an age on it. I mean, I go back to my first slide. Okay, any decisions that involve this well-being of human race has to be done with a little bit of calculation, with some information about what could happen. Okay, if you want, you can go always to the most conservative opinion, in which, okay, if this could happen, I have to protect myself. Okay? The other way around of saying, okay, models are not useful, people is doing crap, etc. Okay, yes, and so what? What we do? We expect doctors in medicine to solve a pandemic? No way. I mean, they are able to cure people, okay? There is another scale, you know very well, about the fight against the coronavirus. But at the level of the epidemics, there is nothing else than models that can help you to project what could happen and what you can do. And then you decide. I mean, there is no model that says you have to do that. You inform policymakers, and then they decide, because there are many, many other considerations in the problem. It's a very complex system, as you know, and socioeconomic implications of this and that is really, really hard to take decisions in this aspect.
Okay.
But
thank you. You completely answered the question, but I was also looking for a discussion about maybe we are in a point in which we can add some kind of confidence intervals for our predictions, and then we can say, okay, up to this point, let's say 3, 4, 5, 7 days, we are very confident that the curve is going to grow, or is going down, or it remains flattened. After that, I cannot tell you, because then 5% of confidence give me one thing, 95% confidence give me another thing. So the problem of predictability or unpredictability is always solvable if we use in our advance these stochastic parameters. So it is something that I think Alex Vespignani was writing in Nature, that this is also improving our knowledge about the mathematical modeling and the necessity that we have. So in order to make a better orientation to these politicians, I think that they will gain more confidence. They will say, okay, because people were asking me what you would say about, I don't know, the next autumn. Okay, just ask meteorologists and you will obtain the same answer. I don't know. So that's the point that I was wanted. But yeah, thank you.
That's totally true. Yeah.
Thank you. So there is another question, and I'm going to ask this one. But it's not me who's asking. It's Álvaro Corral. It's sort of philosophical, and it's the following. I mean, is epidemiology a part of medicine or a part of mathematics or a part of physics? So now epidemiology as a practice seems to be dominated by physicians like Dr. Simon, right? But how do you see, what kind of future do you see for this? Do you see physicians interacting more with like complex system scientists, for instance, or what?
This is a very good question. I don't want to put epidemiology in a box. This has been done many times by people in medicine especially, but I think that the modern centers of epidemiology, they take advantage of all the knowledge in medicine, in physics, in mathematics, in computer science, etc. We are confronting one of the most important projects of human race to fight from our survival against pandemics. And I think that the effort necessarily has to be an interdisciplinary meeting of different disciplines, and complex systems for sure will play a very, very relevant role in this situation. I will not say that epidemiology is from this field or has to be done there. I think epidemiology nowadays is a problem of complex systems, data science, clinical knowledge, medicine, computer science, etc.
Okay, perfect. So I'm going to, I don't see any more questions in the chat, but I want to ask one final question if I'm allowed. And well, yeah, thank you for the talk. I think it's, I mean, it's great work. But I was wondering, there has been like, I guess, also like a search of people not necessarily trained in compartmentalized models to model epidemics and the spread of diseases. And as is this other, you know, branch of like computer science / I don't know, machine learning, whatever you can use to make predictions about things. Okay, so how do you see the interaction of the kind of models that you use with these other models that just learn from data without any biological input? Do you see like interaction between both? Do you think that one can complement the other? Do you think that they can be used to strengthen the approaches that there are now, or no?
I'm totally sure they are complementary and necessary. Because look, in our models, there are a set of parameters that has to be calibrated. That means that you have to assume what is the value according to, in our case, a Bayesian inference method. Well, and there you have all the technology of this part of the computer science that you were mentioning, machine learning, etc., to help you to determine what are the best parameters according to the data that you have observed that is not directly this parameter, okay? You observe incidence, but your parameter is what is the infectivity of the virus, okay? And here, let's say the link between these two approaches is clear. In the other way around, if you use machine learning tools to predict what will be the next number of deaths or the next incidents, you need a training process, right? And for the training, most of the time, what you have at the very beginning of an epidemic is that nobody knows. We have to wait because we are learning with the pandemics going on, right? But if you have a model, you can project the scenarios and you can teach to the machine what the scenarios are promoted by the model. And you can use both in a way in which your prediction can be enhanced more and more. I see this as a new era of epidemiology in which artificial intelligence and mechanistic models have to join together and make something stronger, for sure.
Perfect. So, I lied. There is one last question.
Thank you, Alex, for the presentation. So my question is on mobility and contact. So as far as understood, you have the mobility at the municipality level. But of course, I mean, my question is about how you estimate the number of contacts, because that's the important bit for the epidemic and for the model. And of course, the places that has lower density, they will have less. I mean, the number of contacts is not linear with the density of people. So I wonder how you introduce this bit in the model, so that the places that has low, like higher density, how you expect how you compute the number of contacts in these places.
Okay, thank you very much, Antonio. This is a very, very good point. It's a technical point. We do have a function that is controlled by density about the number of contacts. What we did is the following. At the very beginning of the epidemics, there is a beautiful paper in PLOS Computation and Biology that they reported the average number of contacts per age strata for 111 countries or something like that. I mean, it's huge. You can find every country in the world, okay? And they have, for example, that here in Spain, you have an average of adult with adults is 30.3 contacts per day. You have the same for kids, you have the same for old people, etc. Then we put all these data in a function that is weighted by the density, and then this is exactly how the number of contacts in different regions can be counted. The thing is that when you impose mobility restrictions, what we did is to say, okay, to whom these restrictions will be affecting, okay? If it is for kids, and you pick the kids at home, then you reduce the number of contacts with other kids, with other adults, with other elderly, etc. And then you pick the number of contacts that you will have within the household, okay? That essentially, from also data from the Institute of Statistics, is 2.3 contacts in average, okay? Then, at the moment that you can include these people at home and you can reduce the number of contacts, then the model is producing something in which the chain of contacts has been reduced. And as you said, even at the municipality, if you don't make any lockdown, you can weigh differently according to the density in the municipality. But yes, this is the point. The mobility enters because the number of contacts is the key point in this epidemic process. Yeah.
And also, like when you model the confinement, it's not this. I don't remember the name of the parameter, but it's not uniform in the whole population, I guess.
No.
Take into account that there were, like, in the 3 groups of age that you had, the confinement was different. It was not uniform. Okay.
Yeah.
Cool. Thank you very much. Thank you.
Thank you very much, Antonia.
Okay. So I think that was the last question. I guess we are all. I have everybody join me virtually, thanking Alex for this very nice talk. And also thanking everybody who asked the questions, because I think, they help, clarify some points and learn some more things. And I hope you enjoyed. And well, that's all for today. And thank you very much, Alex.
Thank you very much. Bye-bye.
Thank you very much, Alex. Thank you very much, Marta, for conducting the presentation. Alex, okay, it was a pleasure having you here as a member of our community. You know it, and what's really I think is very good for learning from this set of webinars, it's, as you were saying at the end, is that we are really in an interdisciplinary challenge. And actually, this is okay, I'm trying to see myself. Okay, and I think this is really the point, so that we need to really to make an interdisciplinary community to deal with these so serious problems that science is facing nowadays. So it has been a big pleasure to have you here. So, well, you're supposed to be a physicist in a computer science department. Last week we had microbiologists working, let's say, in a computational biology, and then we had also an engineer, and also had Manlio, who is also a physicist working in a complex system science. And in the future we will have mathematicians or chemists, or I don't know exactly what can we say about Ernesto. He's a little bit of thing. Well, but in any case, it was a pleasure having you here and having all your people. Please remember, next week you will be free Thursday afternoon, so you can take a nap, you can do whatever you want, you can take a walk, you can do whatever you want at 4 o'clock. But in 2 weeks, July 16th, don't miss Ernesto Estrada talk, please. It will be a pleasure to have him here. And remember again, so we are putting all these videos in a special YouTube channel that's devoted to this, and then we hope at the end okay, we will prepare something special for all of you that have been being around. And okay, and thank again all the speakers we need. We know how busy you are, and being a pleasure to have you here. Alex, Marta, and all of you, thank you very much for being here.
Bye-bye.
Bye.